Hey Algebra 2, here are the notes for 14.1 day 2. So now that we know what the graph of the sine function looks like, we're going to try to graph its reciprocal. Now if we look at this on Desmos, what this is going to look like is going to be a little weird. I'm going to draw a little dash line here. It's going to start at 1, and it's actually going to be just the opposite of sine. So what it's going to look like is actually a parabola that starts at 1 and goes up. And then as our sine function goes like this, it's basically going to touch the sine function right there, but it's not going to want to be anywhere near it. So then as our sine function scoops down over here, we're going to see the same thing, and we're going to have another parabola, but it's going to start at -1 and it's going to scoop down in the negative direction. And then that would continue on. So at 90 degrees, it's going to scoop up. At 270 degrees, it's going to scoop down. At 360 and at 180, we have these asymptotes. So the period of the function is still going to be 2 pi. It still takes 2 pi to get our 2 loops. It also takes 360 degrees. And what are the max and min values for the cosecant function? Well, our max is going to be infinite because obviously it goes up forever. And the min, because it goes down forever, is going to be -infinity. Now remember, our max and min for our sine function were just 1 because that's as high as they could go. So I'm going to scoop the sine function in here for us so we can actually see what that looks like and what's happening right next to the cosecant function. It looks something like that. So it makes sense that our cosecant function, if it's the reciprocal, is just going to do the exact opposite of what our sine function is doing. So what do you think is necessary to sketch the graph of the cosecant function? Well, I find that the sine function helps. So I'm going to put sine function. Not necessary, but certainly helpful. And then the other thing is the vertices and the asymptotes. So we know that the vertices of the sine function are going to be our maxes, our mins, and our zeros. So anywhere you have a max on your sine function, that's going to be a min on your cosecant function. Anywhere where you have a minimum on your sine function is going to be maximum on your cosecant. So the vertices are going to be helpful. Anything that's a 0 then is going to be an asymptote. Asymptote. And you can write that if you want. So zeros become asymptotes. And then I just said that the mins are going to become maxes. And maxes are going to become mins because, math turns everything on its head, right? So having each of those pieces is going to help us. Notice when I then go down to graph the secant function, it's going to help to have that exact same thing. So I'm going to start up here at 1. I'm going to swoop down, swoop up. Oop, I guess I didn't go quite all the way down to 1. But that's what our cosine function looks like. So our sine function is going to have that same max, but it's going to be a min for the secant function. Here we go. I'm trying to get my asymptote right there. Because this is a 0, that means that's going to be an asymptote. Notice our other 0 over here, also going to be an asymptote. So I'm just going to put those asymptotes in right away. Then because this is a minimum on my cosine graph, it's going to be a maximum on my secant graph. And I know that I have a parabola trying to scoop away from that. And then just because this is another max, I'm going to put the other half up here. This is still 90 degrees, still 180, still 270, and still 360. So if we notice how long it takes to get a full 2 loops, it's still going to be 360 or 2 pi. So a period for our function in this case is still going to be 360 degrees or 2 pi. And just like the max and min values for the cosecant function, our max and our min for the secant function are still going to be negative infinity and infinity in the max. What do you think is necessary to sketch the graph? Probably the same things. I find the cosine functions helpful because it shows me where my maxes, mins, and zeros are. And then again, the vertices and asymptotes are going to tell me what direction to go and where to start. Asymptotes is a fun word, so if you have a hard time spelling it, please don't feel bad. All right, let's hop over to the back. Now that we have those pictures, we get to do the best one. And the best one is going to be cotangent. So how do we find the tangent? Well, we're going to fill in this chart starting off. We know that tangent is sine over cosine. So 0 divided by 1 in this case is 0. Anything divided by itself is going to be 1. Notice 1 divided by 0, we've got an undefined spot. And when we have undefined, that automatically leads me to know that that's going to be an asymptote. And we'll see that on a graph in a minute. All right, at 135, we've got something divided by the negative version of itself. That's a negative 1. Something divided by negative 1, still 0. Negative divided by negative, just 1. We've got another undefined, a negative 1 here. 0 divided by 1 is still 0. Now, if we actually graph this, instead of just hoping that it lines up like our last two did, the last two were a little bit nicer, this one's going to be a little more confusing. And in fact, I already have to fix it because those values are not right. Let's see if I can find my whiteout here. This. I'm actually not going to go 90, 180. I'm going to go a little bit further down so that you can see just how individual this gets. All right. Instead of going from 0 to 90 right away, I'm actually going to go 0 to 45 to 90. After 90, I'm going to go to 135 and then 180, 225, I believe. Yep, 225 degrees, and then 270, and then we're not going to go all the way up. I'm not going to fill those in quite yet because they're not dry. But what is happening at 0 degrees? Well, based on our graph, or our table up here, we start at 0. At 45 degrees, we go to 1. At 90 degrees, we are undefined. So I know that there is a asymptote right here. Let's keep going. At 135, I'm at negative 1. At 180, I'm at 0. At 225, I'm at positive 1. And at 270, I'm undefined again. So if I connect these dots, what's going to happen is they're going to try to scoop towards each other, but they're going to end up getting so close to these asymptotes that they start to swoop like this. I'm going to connect my other dots over here. They swoop towards each other, but then they end up almost as if by that repulsive magnetic force, they're pushed away. Instead of going in that positive continued direction, they're shoved upwards by that force. So what is the period for this function? Well, it doesn't actually take us a full 360 to repeat this one. It only takes us from 90 degrees up to 270, which is 180 degrees or pi radians. What are the max and min values for the tangent function? Well, because they go up forever based on these asymptotes, our max is going to be infinity and our min is going to be negative infinity. Notice all of the reciprocal functions share that. In case you're like me and you want to see this go off in the other direction, it looks like that. And you'll notice this does continue over here as well. So these periodic functions would continue. So what is necessary to sketch the graph of the tangent functions? Well, the asymptotes come in handy again. But the vertices don't help us as much as the x-intercepts. So I'm going to put the x-intercepts because those tell us where the middle of our graph is going to be. If we know where the middle is, we know that the two pieces on either side are going to be +1 and -1, and then they're just going to swoop towards those asymptotes. All right. Finally, if we use the tangent graph from above, we're going to graph cotangent now. And the cool thing about cotangent is it actually just takes these and it flips them backwards. I think I was saying cotangent before, but what I meant was tangent. I got so into reciprocals, I may have made that mistake. My apologies. Same things happen though. We start at 45, 90, 135, 180. I know there's a asymptote there, so I'm gonna put one there. 225, and then 270. So if I graph the reciprocal, I know that it does the exact opposite. At 45, it still touches a 1. At 135, it touches a -1. And at 90, it touches the middle. So all we've basically done is we've shifted our asymptote over to 180, and we've flipped those. So this flips towards the asymptote, just like that. And then it would happen again over here. It would start by coming down. It hits here at 1, moves up towards the asymptote, and then heads off at 360 in this other direction. So if you look here, let's see if I can zoom out. There you go. You can see both of those graphs next to each other. All that happened here was the asymptote moved 90 degrees over, and our actual graphs flipped the other direction. All right, I know I threw a lot at you. Whatever way you need to remember these, go ahead, but couple things they have in common. The asymptotes and the x-intercepts, or the vertices, depending on which reciprocal function you're talking about, are always useful. And the max and the min of these is always going to be positive infinity and negative infinity. And also it's sometimes just helpful to graph the original function. Let me know if you have any questions.